Back, ladies and gentlemen. Here we go with elastic collisions. I've got a mistake here. This is section 9-6 in this chapter. So, to start things out, the definition of an elastic collision. Well, it's a collision between objects where both momentum and kinetic energy are conserved. And it's pretty simple. It's much like the inelastic collisions, with this difference that kinetic energy here will also be conserved. So there will be no change in momentum from before to after the collision, and likewise there will be no change in kinetic energy from before to after the collision. Now, most collisions are not truly elastic. There always seems to be some amount of energy that's converted to heat, converted to sound, or does work. Work gets done often when there's permanent deformation, and for example in a car crash. And so that lost energy means that the kinetic energy that the system had before the collision is not equal to what it has afterward. So it would not be truly elastic. There's a range, there's a spectrum, and there's sort of mostly elastic, mostly inelastic, but you can think of one or two examples where the collision is so elastic that you do just about see all of the kinetic energy conserved. And one classic example is billiard balls colliding with each other. And when the billiard balls collide, you're shooting pool, and you hear a sound when the balls collide. Fine, but and the sound does require a bit of energy to produce, and that energy would come from the kinetic energy of the system before the collision. But it doesn't require much, and so this collision between the balls and the pool table really is quite elastic. There's a tiny bit of heat generated, but not a lot. The temperature does not warm up very much due to those collisions. You might think super bouncy balls also. I'll put it on here. Super bouncy balls. The thing about this, though, is it's hard to judge. When you drop a ball and it rebounds off the ground, it's never going to come back to the same height from which you dropped it. You let it go, hits the ground, and it's going to rebound back up. And on the trip back up, it will, even the best super bouncy ball in the world will never get back up to that original height. Here's your initial height, here's your final height. Well, some of that is simply due to air resistance, right? It's spending a lot of time traveling through the air here and a lot of time traveling through the air on the way back up. And there's non-conservative work done due to that air resistance. But the collision itself, down right there at the floor, it's pretty elastic. There's very little energy given over to the sound that it makes. There's very little energy given to warming up the molecules within the ground or within the bouncy ball. And so it's a pretty good approximation of an elastic collision. Well, another one is this device called Newton's Cradle. I can spell. Sorry about that. Now, I know you've seen Newton's Cradle before. It's this device where you have a series of what are typically steel balls hanging from wires, right? And the idea is you pull one back and release it, and you expect to see some reaction on the other side. There's a series of collisions that takes place, and you expect on the other side, in fact this is what you will see, this. One of them on the end is going to bounce away. And This is a very good example of elastic collisions. There's some sound generated. There's a tiny bit of heat generated. The molecules do warm up a little bit, but there's no permanent work done, and it's just about as good as you can get for elastic collisions, just like the other examples here. Now, I want to look at a rather straightforward example of an elastic collision, and in this example, I'll call it a simple example. So in this example, I'm going to have one object moving, and it's going to bump into another object which is stationary. So the initial conditions, one object moving, and one object stationary. And so we'll keep those two little initial conditions in mind. We're going to expect that the initial momentum equals the final momentum of the system. And when we expand this, what we see is a couple things. We have m1 v1 initial plus m2 v2 initial. And these two terms are simply the total initial momentum of the system. We have two objects, each one potentially with its own momentum. And the final momentum of the system, well, there's going to be m1 v1 final, and we have to add m2 v2 final. But one of the initial conditions was that one object was stationary, so that goes to 0, and it simplifies a bit because of that. Now, we also expect not only conservation of momentum, but conservation of kinetic energy. So we have an initial amount of kinetic energy for the system. We expect an equal amount of kinetic energy after the collision. So 1/2 m1 v1 initial squared. And I'm not going to write the second term here. I already know that m2 is not moving, so I can just sort of ignore this. It's this. If m2 were moving initially, I'd have to include the second term here for initial conditions, but I don't. Not this time. But this equals 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. Okay. Now, typically, in a situation like this, it'll be presented as a problem for students to solve. And when it's given this way, as you know, you're given some conditions, you know something about the objects, what's going to happen after an elastic collision? Well, the thing that they're asking for when they say what's going to happen is they want to know the final velocities. What's the result of what's going on here? So you see these final velocities, both of them show up in both equations, right? This is giving you two different unknowns, and if you only had one equation, two unknowns doesn't help you a whole lot. But you've got two equations and the same two unknowns. It would be solvable. The textbook sort of mentions that this would be some messy algebra to get there. And don't worry about it. I wouldn't worry about spending time trying to get these two equations combined and solving for one in terms of the other and then resubstituting back into the first. And no. Now, as a result of these two, though, these two equations, we get two unknowns and some expressions for each one. So velocity of 1 final, and we're going to have velocity of 2 final. So the first one, it turns out, is related to the masses in this way. We have m1 minus m2 divided by m1 plus m2. And that entire fraction is multiplied by the initial velocity of object 1. Now this is interesting because that's the only initial velocity that really existed in the first place. This is how you erase Sharpie. There you go. So you can think of the initial velocity of the whole system as simply being that one initial velocity, because one of the objects was stationary, it had no velocity initially. And this is an interesting way of looking at it. The final velocity of object 1 is some related to initial velocity by some term here, and that term has to do with the masses. Well, the final velocity for object 2 is also given by a relationship to the initial velocity, but the business with the masses is different. So the final velocity of object 2 is still related to that initial velocity of object 1, but it's related through this term here, twice m1 divided by m1 plus m2. Okay, now these two equations right here, you're not expected to memorize those two equations. However, you want to be able to work with them, and really with enough practice you're going to end up just about having them memorized, knowing them by heart. But there's stuff going on here, and as always, I don't want you acting robotically. I don't want you just memorizing a formula and using a formula to crank out an answer, and you don't know what's going on. So we have to delve into this and look at some of the significance of this. So if you want to try to give this a go before the video continues, it's page 3. Go ahead, pause the video, and see where if you think you can figure out where we're going to go with looking at these two. And we'll get you there one way or another. So the deal is this. We have to look at those and say to ourselves, well, what's the possibility here? If I look at this subtraction in the numerator, then if I have m1 greater than m2, then this subtraction leads to a positive result. And the whole fraction is going to be positive, and therefore the final velocity will be positive. If I have m2 greater than m1, this subtraction leads to a negative result. The fraction has a negative value, and the final velocity will be a negative value. The third way to look at this is if the two masses are equal. So if they're equal, well, the numerator here becomes 0, and fraction becomes 0, and therefore the final velocity of object 1 would be 0 if the masses were equal. And that's what we expect to see. And we'll do a similar kind of thinking through for velocity of object 2. We can say to ourselves that final velocity of object 1 has 3 possible outcomes, right? It can be a positive final velocity, a negative final velocity, or 0 final velocity. And it depends on m1 and m2. So this means that cart 1 can stop. It can rebound backward if the final velocity is negative, or it can continue forward if the final velocity is positive. And so let's look at this whole deal that we have going on for the final results of object 1. It's going to be a positive value, and that means that here I'll list a result that we observe. Then object 1 will continue forward, and what is it about the masses that leads to that? Well, you get this result if you have m1 greater than m2. Now likewise, your final velocity can be negative, and in this case the result you would observe is, you could say, it rebounds backward. In other words, it's just heading back in the negative direction, and that's, mathematically we got a negative answer for that final velocity. Well, this will happen if we see that m1 is less than m2. And it is possible for the final velocity to be 0, for object 1, for mass 1, to simply stop. And what happens is, well, it doesn't go anywhere, right? this is what's going to happen if m1 equals m2. And we can see that from looking at this relationship right here. I'm going to hide that one so we're not confused. m1 and m2. If they're equal, we get 0, no final velocity. m1 is larger, we get positive answer, positive. m1 is smaller than m2, you get a negative answer, negative direction, it rebounds. Okay, so that's what can happen to the final velocity of object 1. And so let's look at, real quick, let's break this down. Here's like the general results, and I know you've just seen it, but it's worth checking out in some more detail. Here we go. So we might have equal masses. Okay. So let's work this out. We have final velocity of object 1, and if the masses are equal, they're both equal to m. So m1 equals m2 equals just m. The equation becomes m minus m divided by 2m and multiplied by the initial velocity of object 1. Well, m minus m gets you 0, so the whole thing is 0. Not going anywhere after the collision. All right. What about the final velocity of object 2? Let's look at this under these conditions. The equation goes to 2m divided by 2m times the initial velocity of object 1. Well, that fraction just becomes a 1, so the result here, the final velocity of object 2 is equal to the initial velocity of object 1, and they have pretty much sort of exchanged what's happening here. Look at this. Well, for this situation, object 2 had an initial velocity of 0. Now object 1 has an initial velocity of 0. We saw the trade. Okay. Not scientific, but we can understand this easily. Rigorous. And make sure you can see what I'm doing when I set the masses are equal to each other. I'm simply coming from these two equations here. Remember, this is what we're trying to do right here. This guy. This guy right here. Now, what if the masses are unequal? Okay, now I'm going to say more than unequal. I'm going to say, what if m1 is not just greater than, but significantly greater than m2? A lot greater than, 100 times, 1,000 times greater than, something along those lines. Now, there's another way to look at this, or to think of this situation. To say, or, what happens as m2 approaches 0? Okay, that's interesting. Not m2, not necessarily is 0, but you know what I'm going to have to do when I say this in the equation? I'm just going to have to write a 0. So here's our condition of the two masses, and I'm going to reevaluate final velocity of object 1. And I'm going to say to myself, well, okay, I have m1 is much greater than object 2 than m2, or that m2 goes to 0. This becomes m1 minus 0, or just m1, right? And so, and I'm dividing by m1 plus 0. A little sloppy, sorry. Now, check this out. This fraction simply equals 1 at this point. So, now, but remember, it's not exactly 0, it's just approaching 0 mass. Or the difference is large enough that the mass of object 2 is insignificant, right? So I'm going to put these squiggly lines instead of an equal sign. This means approximately. So this is approximately the initial velocity of object 1. So what is this telling us? That object 1, v1, is mostly unaffected. Okay, that's one way of looking at this. Look, final velocity of object 1 is roughly equal to the initial velocity of object 1. The velocity of object 1 is mostly unaffected. Okay, object 2. What is this going to look like? When we say that m2 approaches 0, we have 2 times m1 divided by m1 plus 0 multiplied by the final velocity of 1. And now, so again, squiggly lines to say that this is approximately equal to, and this is interesting, this fraction ends up having a value of 2. So 2 times the initial velocity of object 1. So what's another way of looking at this? The velocity of object 2 is nearly doubled. Or not doubled, double that of object 1. Nearly double that of, here we go, object 1. Okay. So now there's one last set of conditions to evaluate. And I want equal masses. Mass 1 is significantly greater than mass 2. And now we're going to reverse that. We're going to say that our final set of conditions that we'll explore, M2, is going to be significantly greater than M1. Now, just like the other one, I can say or M1 approaches 0. Okay. There's our conditions for the masses. Now, once again, evaluate final velocity for object 1. So, just like before, substitute 0 for M1. So we have 0 minus M2 divided by 0 plus M2 times the final velocity of object 1. And this is going to be approximately equal to, remember, approximately, it's got to be approximate. And so this fraction looks like it's going to be equal to negative 1, so we have negative initial velocity of object 1. And when you look at this, you started with, it started with a positive velocity and now has a negative velocity in equal amount. So what are we saying? That M1 reverses direction or rebounds, reverses direction at nearly original speed. So it's quite interesting. It's a rebound. It's a rebound, and it's traveling backward now at a speed that is nearly equal to the speed it had initially. Now we're going to evaluate for object 2. And again, where there's an M1, I'm going to put a 0. So 2 times 0 in the numerator, and here's 0 plus M2. Multiplied by the initial 5. Okay, you know what? Just realized I screwed that up. That should be initial velocity. Sorry. Erase. Now, initial velocity, here we go. Oops. Also, we're approximating here. This is roughly equal to, because M1 isn't equal to 0, but it's approaching 0, or it is so much smaller than M2 that it really is like being 0. Well, anything times 0 is 0, this is 0, that's 0, this is approximately 0. So what we see after the collision is that M2 barely moves. It's hardly affected at all. And the larger the difference in the masses, the closer to 0 this becomes. Alright, this is some interesting stuff, interesting results, and also keep in mind that I always want you doing this, and since you're doing that, you'll realize that we've really only explored one set of possible initial conditions for the motion, right? And we could set up other possible conditions. But this is some good stuff to work with for now, and we'll make it happen. Thanks for watching. I will catch you next time.